have noticed that the due date has been extended on this, on chapter, what chapter are we in? 2, 3, something like that, 2 vectors, on the vectors chapter. There are several people that had questions about things, and so I extended the homework until I think Saturday, which would be tomorrow. So you have some extra time to work on those things and to ask questions. I think in particular, the most of the questions that I had involved kind of maybe the difference between dot product and cross product and kind of how they're used, what they're used for. There's a particular problem, I don't remember which one it was, that had a couple of questions that involved 2 vectors, and they talked about said something like, let's see if I can find it here. It'll be towards the end here somewhere. No, that's not right. So this one right here had some questions. The component of vector B along vector C. This is what I was talking about when I was talking about projecting one vector onto another vector. So if you want to find how much of a particular vector points in the direction of another vector, you use the dot product to do that. But the dot product is not the end result of that answer, because the dot product actually tells you the product of the vector pointing in the direction of another vector with the other vector. So if you want to find out the component, you need to divide by the magnitude of the vector that you're taking the dot product with. So for part A, for example, this one would be the dot product B dot C, and then you divide by the magnitude of C to get the component of B in the direction of C. So that's, I know that that's not necessarily, it's certainly not intuitive. It's not something that just makes sense to us, and it's hard to explain it without doing it. But what you're doing when you do this particular part of the problem, let me bring up what the dot product is doing for you. Let's say that we're doing this very first one, B, the component of the vector B along the vector C. So here's the vector B, and here's the vector C. So these 2 vectors are 53 plus 60 degrees apart. So that's 113 degrees apart. And if I drew them over here off to the side, it would look more like this. Here's my coordinate system. And the vector C is 60 degrees down this way. So it's, ooh, not a very straight vector. So that's the vector C. My vector B is 53 degrees up this way. So it's more like that. So they're definitely more than 90 degrees apart. You can see that fairly well, I guess. But what we're going to do is we're going to project B onto C first. And so it's like we're shining a light over here with these parallel rays of light coming in here, and we're going to cast a shadow along C. Well, B is pointing over here, so we have to extend our C vector to show us how this projection is going to work. This B vector is going to leave this shadow, this perpendicular shadow that's going to look kind of like that on this C vector direction thing going here. And what the dot product is going to do, it's going to take this right here is the B vector that is projected onto C. The dot product is going to be that B sub C component times the C or magnitude times the C magnitude. That's what the dot product B dot C does. But we just want to know this B component along C, this B sub C thing. So we need to divide by the C vector to get that answer. Now you could also do it by just projecting it, by just saying, oh, I'm projecting this here. This is my hypotenuse. So my hypotenuse is B, and I need to know That's the magnitude of B here. And I need to know this vector, so I need to take this angle, and this would be the cosine. So I would take B, B times the cosine of whatever that angle is, and that would also give me B sub C. And to figure out this angle, you need to know this angle. Well, this angle was 113, so you take 180 minus 113, and that would give you the same answer. So either way you do it, you'll get the same answer. This one uses essentially a drawing and some trigonometry. This method uses the actual definition of the dot product, and then you divide off the C magnitude there. And that's basically the idea behind these kinds of problems. Did anybody else have any other problems that they would like some clarification on or some understanding of before we are done here? If there's a problem that you haven't been able to get done right in the homework, or you just have a question about, any clarification on any of the ways that we deal with vectors, arithmetic of vectors, algebra of vectors. There is one other one that I think I should probably point out, and that is this. Let's see. Yeah, this one here. In this one here, you're given a bunch of vectors, and then they say, what is R if D plus R equals F, right? So you can do this math. It's just pretty simple algebra, right? You're going to solve for R by subtracting the D vector from both sides of the equation. And that's perfectly legal to do. So R ends up equaling F minus D. And then you just take the, then you can do this using the components of the vectors. So you take your F vector, and the F vector is going to have an X component, which is going to equal the magnitude of the F vector times the cosine of the angle theta. All these angles are measured from the X axis, so that's legal. Now, the thing that you have to be careful of is you have to make sure that your, so this F vector is pointing downward to the left. So in the end, this one will have a negative on both the X component and the Y component. So when I do this, some people like to just use if you use the angle from the positive X axis, so this angle here, instead of using 30 degrees, you use 180 plus 30 degrees, then you can just use theta here and it'll give you a negative sign when you're done. Because the cosine of 220 degrees, 210 degrees, which is 180 plus 30, is a negative number. So this will just give you a negative value in front. Personally, I just like to remember that needs to end up negative. So whatever a number I get out here, if it's positive, I just throw a negative on it. If it's not, if it's negative, I just know that it worked out. You can do it either way you want. It doesn't really matter. It's good to make sure that you know that if you have a coordinate system that is like this, that is going X out here and Y out here, which is our standard coordinate system, and that's the one that they chose here, then you need to know that this is going to have two components that are going to be negative, negative, because it's in this third quadrant or whatever that is. So you just need to know that to make sure that it ends up that way so that you don't mess things up. And so that so this equation here in the end becomes two different equations. This becomes R sub X equals F sub X minus D sub X. And this, whatever number you get out of here, which is a negative number, will end up here. So you're going to end up with some negative value for F sub X here, minus the D sub X. Go look at D. It also has a negative X value, but it has a positive Y value. So this equation here is going to end up being negative something, negative some number, minus the negative some other number in the end. And that's going to give you some negative values for R sub X. And then you do the same thing, F sub Y, right? The F sub Y is going to be, for F, it's going to be a negative number for sure, sine theta in this case. And then you're going to have an equation R sub Y equals F rather sub y minus D sub y. And when you get done, you're going to have a number for R sub x, a number for R sub y, and you'll combine them to make your R vector here. Your R vector in your answer here is going to look like the whatever number you got for R sub x times I hat plus whatever number you got for R sub y times j hat. And that will be your R vector answer. Any more questions about that? We understanding that okay? Okay, does anybody think they'll need more time than tomorrow night? We could put this on to like Sunday night or Monday night or something. Think we're okay? Anybody online prefer a little more time? I think I might just move it to Sunday night. It makes no difference really. Let's just move it to Sunday night just to be sure. I put it on the 12th. Seems like a bad omen to have homework due on 9/11 anyway. That's not what I want to do. Okay, so this homework will make it due the 12th. But don't wait until the last minute to work on it. It's harder that way. And also, I don't answer emails on Sundays. So if you have questions, make sure you ask your questions before, like Saturday afternoon. I also don't generally answer emails very super late into the night. So if you ask your question at 11 p.m. on Saturday night, it's not likely that you'll get an answer back until Monday. Make sure you work on that. Last call for any questions. Last chance to ask a question for this homework, to get a problem kind of demonstrated or anything. Any last requests before we move on with life? Okay. If there are no requests, then we will move on to something new today. And that is the labs. We want to, I need to, so we have this form. Let me see if I can get into it. I'm pretty sure that I can. Let's go to DocuSign. I'm going to send you each an email with a form to fill out and sign. DocuSign login. That sounds promising. How do I log in? Log in. There we go. All right. My password is this password, I think. They just sent this to me, so I've done some things that I need to get done on it, but I'm going to try to do the rest of them right now. Okay, so we're looking at templates shared with me. Okay, equipment checkout agreement. I believe the one we want to use. We want to copy it maybe. We're going to call this physics lab kit checkout agreement. How's that? Used to check out lab equipment. Lab equipment students. Okay. And we want to use this, I think. So in this agreement, we're going to have a number that you'll fill in here. Each kit will have a number associated with it. This here, this is going to be a little bit different because you're going to be putting the deposit down. Let's see. It needs to be a PDF, so maybe we'll just make our own here. Indemnification. Okay. Seems very let's download this and use it for ourselves. You guys get to watch me do this just because it's fun, and I just got it, so I need to get it done. It's part of this, what we're doing in this class. So gotta do it, gotta do it. Okay, so this is going to be our document. I'm going to go ahead and copy all of this. Edit now. I guess I can. I don't know if I can edit. I don't think so. I don't want to mess with that. All right, we'll do it in Microsoft Word. Hopefully Word will be able to handle this. Action should be okay. All in here. It's not too bad. Okay, in consideration of the checkout equipment to me for academic use. It's messy. We'll call this a lab kit number. Run responsibility. I accept responsibility. I'm not going to say full responsibility because I'm not expecting you to replace anything necessarily. I'm just hoping that you will be responsible. Equipment that has been trusted me. I accept responsibility for any loss after damage. Okay, loss, theft, or damage to the equipment will result in loss of part or all of my deposit. $100. And it's not say will result, probably should say may result, because if something small is lost or broken, that's not a big deal. Okay. Indemnification. I agree to indemnify and hold harmless MPCC. Sure, why not? I don't know how necessary that is to include, but apparently they think it's necessary. Let's fix this. Use, I understand. No, we're not going to have to worry about that because we're not doing computers. MPCC. So don't use the physics equipment illegally. This one says it's my responsibility to return equipment, same condition, which is registered no later than Government on the due date listed below. If the equipment is not returned, it will be deemed lost or stolen, and action will be taken as outlined in number 7, lost or theft. Okay. Academic hold and return of the hold may be placed. I may have. Okay. Till I have returned the equipment. Maintenance, repairs, and upgrades. No person. Loss or theft. I can't imagine anybody stealing the physics lab equipment, but whatever, right? Codes, check out agreement, follow all IPCC collection policies. 30 days receive. Do notice hold will be placed on the receipt company access insurance. $40 late. Well, just added. Accounts may be sent to collection agency if the need arises. Okay, we can go ahead and leave that, I suppose. So I'm going to just fix the formatting here really quick. Shorten this thing up a bit. I hate documents that go on for pages and pages. It's just not necessary. In the future, I'll probably shorten this even more. Seems very wordy. Written by a lawyer, no doubt. Okay. Okay, borrower. You don't need to be that extra stuff there. Borrower's printed name, borrower's MPC ID, borrower's address, phone, signature, staff signature, checkout date, upon return. Okay, I guess they did need that. On borrowing. Okay. Let's go ahead and insert a page break there. Okay. And then return to MPCC, review the condition of your value laptop feature. Let's check that out. Sweet lab kit. Oops. One. Two. I think we'll end up with a total of 4 lab kits for the year. And I did talk to the business office and they said that we can just carry over the $100 till next semester. So that's not a problem. Let's see here. Let's give ourselves some. All right. Let's save this. Lab, check out form. Okay. Now we're going to upload and see how we did. Now, if there's anything that you think is missing from this or something that shouldn't belong in this, you can speak up. I may or may not agree with you, but you're more than welcome to give your opinion. This is our first draft of this document. So responsibility, part I lost my deposit, got formatting issues again, but number 2 is you're agreed to hold harmless MPCC. In other words, while you're using this equipment, anything that happens to you or your house or whatever else, your cell phone has nothing, we don't have anything to do with that. That's up to you to make sure that things are kept safe. If we feel like it's being used illegally, then we can cause problems, I suppose. Return that you're going to have it returned by the due date. And if you don't, it can be, we'll go lost, stolen thing, academic hold. You can, the academic hold is actually a pretty big deal because if you're trying to transfer somewhere and you're on academic hold because your kit's not turned in, that can cause you some serious issues. You're trying to get your transcripts or whatever moved. In the maintenance, please don't fix things yourself. We'll fix them. Loss and theft, and you please report that immediately. I don't think it's necessary that you maybe report it to the police immediately, because maybe it's just lost, but we should definitely report it to me so we can try to figure out where we can find it or replace it. And then collections policies, if they end up having to wait if we end up having to wait for the kit to come back a very long time, we will not return your $100, but if it does get returned eventually, there may be a late fee added to that. So that is that. So then you fill out this stuff when you check it out. We'll fill out this stuff when you return it. And then when it's returned, we'll evaluate each kit to make sure everything's there, make sure nothing's broken, and then decide how much of your deposit you get back. Looks like this needs a little bit of formatting fixing, but I think all the components of it. Does anybody have any questions about that form? About what's going to be expected with that form? Okay, before I put it in here for filling out, I am going to modify it slightly just to make sure that the formatting's a little bit better than it was. It's fine, it's this one. And looks like the rest of them are okay. So those are fine. This is a mess. Let's fix this. Oops. All right. Why are there 3 dates for due date? I think we should put the due date somewhere else. I think we should put the due date here. All right. Upon borrowing, upon return, this will be Staff reviewing equipment. Um, oops. Mechanics. So for this class, we probably won't have actually 4 kits. We'll probably only have 3. 2 this semester, 1 next semester. We probably will never use the optics kit. But nevertheless, this looks good to me. I'm going to resubmit that. Oh shoot, that's not what I wanted to do. Can't remember what I called it. All right, now we're ready to go. Let's upload a new form. Newest version. And this is the one we're going to use. Used to check out physics equipment. So I think we're going to I don't know what I'm going to do with that. So I'm going to add recipients here. I'm the instructor. You guys are the students. You will need to sign. So I'm going to put all you students in here. We'll go back to my WebAssign page and get your emails. So anyway, this form will come to you as this is. The due date, I will put as the last day of the class in spring for the due date. And then when it comes to you, it'll come as an electronic signature form, which you'll click on fields and fill out your stuff, fill out your information. Then there'll be a signature field that you'll click on, and it gives you options for an electronic signature. And then you'll complete the form. It'll come back to me, and I'll sign it and send you the equipment. But then in the meantime, you also have to take that form, I believe, or at least you have to just go down to the student office, the student accounts office, and tell them that you're paying, you need to pay for your lab kit, and then that form will be completed at that point, and then then you'll get your lab kit sometime next week. Any questions about that? I think there's a couple more things that I have to do here in the background to make sure that it goes to the right people, because I think that I need to sign it, and then I will send it to you, and then it will go to student accounts, I think. And then they'll sign it when they get your $100, when they get your $100 deposit, and then it'll go to, and then it'll be completed, I guess, and then I'll be able to mail everything out. Does that make sense? All right. This is a lot of trouble, but we'll live with it. All right, so I'm gonna go ahead and leave that aside for now. We're more than halfway through our class time. We are starting next week, moving on to actual physics, which is exciting. We get to actually do physics. If I can find the chapter we're doing here. Motion along a straight line. And I'm going to go ahead and start that for today so that we can kind of be ready to fit. We'll try to get through all of that next week. There are 6 sections, so try to get through 1 or 2 sections here before we leave. We start motion in one dimension because the math is easier than motion in 2 dimensions, obviously. But we also start in 1 dimension because the math and the physics transfer into 2 dimensions. So we can, if we can learn how to do this, all the stuff in 1 dimension, and then we can learn how to break 2 dimensions and 3 dimensions down to separate dimensions, then we can use all the skills that we used in this chapter separately in individual dimensions. And it just is nice that way. The reason we can do that is because we choose dimensional coordinates that are 90 degrees to each other and completely independent of each other. So we love that. Start off with then, actually we'll go back to the picture here on the previous page. Gotta love the bullet train. This one is the JR Central L0 Series 5-car maglev train on the Yamanashi test track. So the maglev trains, maglev stands for magnetic levitation, and they work differently than most people understand. Most people don't understand how this works. In fact, I would go as far as to say it's probably only engineers that are electrical engineers for the most part and physicists understand how maglev trains work. But they work on this they work on a principle that's quite interesting called magnetic induction. You may have heard this term. There's my magnetic induction. Must be in my office. I'm going to go to my office really quick and grab a demonstrator. Can't find it in my office either. I don't know where it is. I have moved it somewhere and not kept track of it. Well, that's okay. Oh, it's right there. Right where I was looking. Okay, here it is. So this is a demonstration of magnetic induction, which helps us to understand a little bit about what's going on here. If you look at my personal camera, you should be able to see this. Let's see if I can do this. I don't know if I can, but anyway. So what we've got here is we've got 4 different rods here made of different materials. This is plastic on the end. This is brass, this is aluminum, and this is copper. Why do we have 3 different metals? Well, these 3 different metals have 3 different conductivities that conduct electricity differently. Copper conducts at the best, aluminum second best, brass third best, and plastic doesn't conduct electricity at all. On each of these tubes, there is a ring magnet, a very strong ring magnet that I'm holding up with my finger here. And on the plastic tube here, you can see that it just, if I lift it up to the top, it just drops. But not so with the metals. If I lift this one up on the brass, it drops, but it drops maybe not quite the same way. If I go over here to the copper, you can definitely see a difference. It takes time for it to drop. Definite amount of time. So if I flip this thing over, you can see that the one on the plastic on this side drops very quickly, and then less quickly, and then very slow, right? It goes boom, 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 right? Why do the magnets drop more slowly on the metals? Well, people immediately say, well, because the metals are magnetic. Brass, aluminum, and copper are not magnetic. Not at all. In fact, they're the antithesis of magnetic. They actually lower magnetic fields when you bring a magnet near them, whereas magnetic materials strengthen the magnetic field. If you bring a magnet near steel or iron, the magnetic field of the magnet that you bring close to it actually gets stronger. It actually increases because the steel becomes magnetic. So these are not magnetic metals. So why does the magnet slow down? Well, the simple answer is that moving magnetic fields or changing magnetic fields cause currents to flow in metals. And those currents create new magnetic fields which oppose the moving magnetic fields or changing magnetic fields that are causing those currents. So the magnet that's moving past a piece of metal actually feels a magnetic field being created in the metal, being created by the moving magnetic field, that opposes it, that pushes against that magnetic field. So the magnet feels an opposing magnetic field that pushes on it and slows it down. If you have a metal that is easier to create current in, like copper, it creates more of that current, right? And that's exactly the idea behind the maglev trains, right? And since you're all, budding and promising electrical engineers, I hope you'll find this interesting. There is a material, a group of materials, a class of materials called superconductors, that when you have them in the correct conditions, they have zero resistance. In other words, they have infinite conductivity. I just happen to have some superconductive material right here. This superconductive material is from the Super Collider, the Atomic Smasher Collider in Chicago at Fermilabs. And each one of these wires here, this tiny little wire here that you can see, is about 1 millimeter or less in diameter. But it started as a bundle of 10,000 wires that was like bigger than your head. And it's made of many different things. I think it's made of titanium and copper and tantalum and a bunch of other things, a bunch of different wires essentially. And what they did is they stretched it and twisted it and made an alloy out of it. And they kept stretching it and twisting it until it was this tiny. So this big bundle, they stretched out into this super long cable, and it's very, very tiny now. But that alloy that they created, when you lower its temperature down to about 5 Kelvin or so, about the temperature of liquid helium, it becomes a superconductor. It has no resistance. That means it's infinitely easy to create a current in it, which means if you bring a magnet anywhere near this thing, it's going to create a huge magnetic field that's going to oppose that magnet, right? So what they do is they build a train track made of these superconductors, right? And here's the other thing is that this works in reverse as well. If you have a superconductor and you put a bunch of current through it, then you make a huge magnet. And then if you bring a piece of metal near it, the metal will also have a, so you don't have to have a moving magnet. You can have moving metal and a stationary magnet. It works either way, right? So that's the last thing I should say about this. So they switched this up. Instead of having a train that's magnetic moving near superconductors, they make a superconducting track, because the track has to be cooled by liquid helium, and moving liquid helium is not a good idea. So they make the track out of superconductors with liquid helium cooling down the superconductors. And then they drive a current through these superconductors to create a huge magnetic field above the track. And then they make a train out of aluminum. And they move the aluminum train across the track. And that creates a huge current in the aluminum, which creates a magnetic field, which opposes the magnetic field in the superconductors. And we have two opposing magnetic fields, one from the train and one from the track. They're going to push on each other, and the train floats above the track. But it only works if the train is moving. So when the train is not moving, when it's in the station, it actually falls down to the tracks. And they put wheels on the bottom of the train so that when it slows down and it gets closer and closer to the tracks, it can land. So these maglev trains are not trains at all. They're actually electromagnetic airplanes or electromagnetic UFOs or something. They're actually flying down the track. To get going, what they do is they use the wheels on the bottom, just connect them to motors, and they just start moving the train. And as the train goes faster and faster and faster, the magnetic fields that are opposing each other build up in strength higher and higher and higher. And eventually this thing takes off. It eventually starts to float above the track, and then it can retract its wheels for aerodynamic sake, and it just flies along the track. And they can actually speed up the train or slow down the train by pulsing electricity through the track and cause it to, they can cause it to speed up or slow down. And if it's moving, if the train is moving along and the track turns, if the train tries to leave the track, there will be a magnetic field that is just automatically created by the nature of this idea that turns the train back onto the track. So the train actually can't come off the track in any direction. If it tries to get too high above the track, the magnetic fields will oppose that and pull it back down. If it tries to dive into the track, it will push it back up. If it tries to turn left or right and go off the track, those magnetic fields will steer it right back onto the track. Because that's just the nature of the beast, actually. It's just the nature of magnetic fields, moving magnetic fields. So in theory, these maglev trains are extremely simple. Creating a track out of superconducting materials that are cooled by liquid helium, that is pretty much all of the engineering involved. It's all about the track. The train is the easy part. The track is all that they spend all their time working on this track. One of the biggest things that they do is they try to create materials that don't require liquid helium to cool them, because liquid helium is so expensive. Helium, for one thing, is a rare element. It's very rare. It's very rare to have helium, for one thing. The reason is that helium has a very small mass, and it's always a gas unless you cool it down to like 5 Kelvin, which is difficult to do. And so you have a gas with a very small mass in our atmosphere. It means it's going to have a very high velocity, and it's going so fast, in fact, that it can actually escape the Earth's atmosphere pretty easily. So helium is not something that we have a lot of, and it's difficult to capture, difficult to maintain and deal with. You can create helium, but you have to create it in a nuclear fusion reaction, which is not easy to do. You know, we have nuclear fusion bombs where you can create a nuclear fusion reaction, but unless you're creating helium on the sun, it's very difficult to create. The sun does it just as a matter of course. It's really easy for the sun to do it, but for us, we have to use a nuclear fusion reactor, which is not easy. So this is one of the hot topics in electrical engineering, the idea of superconductor, creation of new superconductors, which is partially electrical engineering, it's partially metallurgy, it's partially materials engineering, because a lot of these superconductors that don't require liquid helium are actually made of ceramics instead of metals. They're more of a semiconductor ceramic material. And we will, next semester, we'll play around with some. I've got some superconductors we can play with. And they're really quite interesting. You can actually make a superconductor float above a magnet, or a magnet float above a superconductor, just by bringing the magnet to the superconductor. If a superconductor, fill it with, my superconductors don't require liquid helium. You can use liquid nitrogen to cool them off. So I put a superconductor in a little bowl full of liquid nitrogen, and then I just move a magnet to it, and that creates enough current in that superconductor to hold the magnet up. And it just sits there above the superconductor until the superconductor warms up, because all the liquid nitrogen boils off. It'll just sit there and just float there. Whatever position I put it in, if I start it rotating, it'll keep rotating. It'll just keep doing that forever. We can actually build our own maglev train. That's one of the projects that I would like to do next semester, where we design and build a maglev train using magnets and superconductors. Use a magnet. We won't use a superconductive track because the superconductors are very expensive. We'll use a magnetic track. We'll do it the other way around. We'll have a magnetic track and have a superconductive car instead. So anyway, the point being is that this is a really hot topic in electrical engineering these days and materials engineering. And once we figure out how to do this, we could maybe make our roads out of superconducting material and have floating cars too. That'd be fun. Everybody wants a floating car. When we're dealing with motion in 2 dimensions, we have to define things. And that's what we're going to do today. We're going to define specific things. First of all, we're going to define position. What do you need in order to define position? We already talked about Descartes, right? So what did Descartes say you needed in order to define the position of the fly in his room? Well, you need a coordinate system, right? You need to decide what your coordinate system would be. North, east, and west, or north, south, east, west is my coordinate system, but you also have to say up and down in the room. So my coordinate system is going to be, east and north or whatever, and up and down, whatever, right? And then you also have to have an origin. You have to have a beginning point to say that's my 0 point. Everything's measured from there, right? And when we do this, then we can start to define position, and position can be a vector. It would be a vector from the origin out to the point that you're trying to define. That vector would be your position vector. And then you have what we call a displacement vector, which is going from one position to another. So if you have one position that is defined as x naught and another position that's defined as x final, we're in 1 dimension, then the displacement vector would point from where we started to where we finished. And the mathematical definition is to take that final position and subtract the initial position, and that will give us the length of that displacement. It will give us the magnitude of the displacement, how far it is in a straight line, but it'll also tell us the direction. If we go final minus initial every time, that will actually tell us the direction. The direction here is in the positive x direction. And this arrow does point in the positive x direction. If we started here and we took this one minus this one, we would actually get a negative 2 meters and would point this way. That would mean that this person walked in the negative direction instead of the positive direction, right? So that is displacement, which is different than distance, right? In 1 dimension, everything's in a straight line because everything's on a straight line. But distance is different because you can walk between this point and this point, but you can go a longer distance. Let's say you walk halfway and then you walk back and then you walk 3/4 of the way and then you walk back and then you walk the whole way. That's a longer distance, but it's still the same displacement because you ended in the same place you've started. You ended, in the same place both times, right? But you took a different path to get there if you walked back and forth and back and forth. So displacement, what happens? What is your displacement if you start and end at the same position? It is 0, right? So if I start in North Platte and I go to Kearney and then I go to McCook and then I come back to North Platte, my displacement is 0 because I started and stopped at the same place, the same position. But the distance that I traveled is 100 miles to Kearney, then another 100 miles from Kearney to McCook, and then 70 miles from McCook to North Platte. That's 270 miles. That's my distance. Distance is always a positive number, and it just tells you how far you traveled along the path that you took. That's all it tells you. Displacement tells you the straight line distance between 2 points and the direction from your beginning point to your ending point. That's what displacement is, different than distance. And displacement can be 0 even if you traveled however far a distance. So that's our first definition, and we will move on to more complicated definitions that will involve this definition and so on and so forth and other things. But that's gets us started, and we'll come back to it on Monday. If you have any questions involving Chapter 2 homework, please email them to me before Saturday evening so I can answer them. And if you want to get started on Chapter 3 homework, it is available. You can go ahead and see what you can do there, and we will finish up Chapter 3 next week. Have a great weekend. We will see you later. Made a mag left turn? Made a mag left turn?
No, just the pipe.
Oh, one of these.
Yeah, I've had several different ones. This is the newest one that I have. I have several that are just pipes that you roll a magnet through or drop a magnet through. Yeah, that one's cool. My favorite one that I'm still working on is a demonstration I had at the college I taught before here. It was just a big chunk of copper that I put on the table, and then a huge magnet I would hold in my fist, and then I would swing my hand at the copper as hard as I could, and my hand would slow down and then only just touch the copper. I never was able to hit the copper. And that one you have to be careful with, because if you don't get enough current flowing in that bottom piece, then you hit your hand. But otherwise, it's because the harder you swing, the faster that thing comes at it, the more it pushes back. So it doesn't matter if you can't swing hard enough to hit the metal, because the harder you swing it, the more it pushes back. But the really interesting one is I have a ring launcher here, which we'll demonstrate next semester, where it creates an alternating current in the Tesla coil essentially, and then you put a ring over the top of it, and it creates an opposing magnetic field in the ring, and then the ring shoots off, and the ring is just made of metal. It's no magnet at all. Yeah, you've seen that one? Well, if you hold the ring down instead of letting it shoot off, then the ring heats up, and you can see that there's current going through it. You can feel that there's current going through it, because it heats up and heats up rapidly. Like you have maybe a half a second before you have to let go, and it's too hot. So that's a cool demo. And I've also got a coil that goes around that, so that you can push the button on the ring launcher, and the coil gets current going through it, and then you can connect the coil to a lamp or a bell or something like that, which demonstrates the idea of wireless charging, right? Probably the coolest demonstration of this recently is actually a demonstration that MIT did. They actually demonstrated that you can charge a phone using the cell phone signals in the air around us. So they've actually developed a battery that can be charged just by itself. It doesn't have to ever be plugged in. And it's not very practical yet, because you can't use the energy on it. The rate that you use the energy is much higher than the rate that it's collecting energy. But that's just a matter of engineering. Eventually they'll get that down so that you can have a phone that you never have to charge. It's just picking up radio waves, and that's charging your phone essentially all the time, which will be really cool. Yeah. So wouldn't it be nice to never have to charge your phone? But yeah, it's cool stuff for sure. It's really cool stuff. So.
Yeah, I was copper pipe. It was a pretty big gauge.
Yeah.
And then I soldered another one around it, and it was crazy.
Yeah.
Because I had like a really heavy magnet. It's really strong. You just go put it down and just.
Yep. See, and I didn't even use heavy magnets. I just use things like these guys. Actually, those are the ones I use. That stack of colored magnets, and they're not super strong. They're strong magnets, but not super strong. And I just dropped it through an aluminum pipe. I have it kicking around here somewhere, and it, you drop it through and wait, falls out finally. Another one that's cool is that I built. I built it. I started building it, but I never finished it, and I still feel kind of bad about it. But I have a good friend who works for Pixar, and he, when he went off to go work for Pixar, he was collecting kind of eclectic little things to put in his office, because it's pretty common for people that work for Pixar to have weird things in their office. It's just kind of a tradition. And I made him this, those games that you can roll the ball around in. I essentially made him one of those, but it's just one that you flip over, and there's two tracks that are zigzag next to each other. One of them has a magnet in it, and the other one has a metal ball bearing in it. And as these things go down, the metal ball bearing, of course, goes. The magnet one just rolls slowly on, because it's made of aluminum. And so the magnetic one will go tick, 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 as it's slowly going down. And this one's. And I built them. I cut out one track on one side, and I started the other one, and I never finished the other track, and I never sent it to him. And it's like 20 years later now. I still have it I have it back there on one of my machines, because I thought, oh, I'll finish it, and then I just never got around to it. I just got too busy. One of these days I'll finish it and send it off to him. He's been in several different places working for Pixar. Now he's in San Francisco, I think, area. So Maybe I'll finish it and send it to him and say, hey, 20 years late, you can put this in your office now.
I gotta be careful.
All right, see you later.
I'll see you later.
Have a good one.